December 29th, 2024, 2:47 a.m. local time. 2 kilometers underground in South Dakota, inside a tank filled with liquid xenon, something happens. For 100,000th of a second, a xenon atom recoils. Energy deposited, 6.5 kiloelectron volts. A flash of light, captured by sensors, recorded. By itself, it means nothing. Background radiation causes thousands of similar events every day. But this one is different. The energy signature matches predictions for dark matter. The location in the detector matches dark matter expectations. The timing is random, as dark matter collisions should be. If this is real, we just detected something that makes up 85% of the universe's mass but has never been directly observed. We just saw the invisible. Or was it a cosmic ray that slipped through shielding? A neutron from radioactive decay in the rock? Background radiation we didn't account for? A statistical fluke? This has happened before, multiple times. Dark matter detected, followed by, never mind. Scientists are cautious, and they should be. This is the story of the most important signal we're not sure we actually saw. The Detector, LUX-ZEPLIN, Sanford Underground Research Facility, South Dakota. Depth 1,478 meters, 4,850 feet underground, roughly a mile beneath the surface. Purpose? Hunt for dark matter particles called WIMPs, weakly interacting massive particles. The detector contains 7 tons of liquid xenon, cooled to minus 100 degrees Celsius, minus 148 degrees Fahrenheit, maintained in ultra-pure conditions. Surrounding it, layers of shielding, water tanks, lead, polyethylene, all designed to block background radiation. When a particle interacts with a xenon atom, it creates 2 signals: immediate flash, scintillation light; delayed pulse, ionization electrons. The timing and energy of these signals tell us what interacted. December 29th, 2024. Event 187,429 since the experiment began. Energy, 6.5 kiloelectron volts. Signal pattern, matches nuclear recoil, as opposed to electron recoil from background radiation. Location, deep in the detector's fiducial volume, the ultra-pure central region. This is exactly what dark matter collision should look like, but so do several other things. 1998. The DAMA LIBRA experiment in Italy reports detecting dark matter. Their claim: an annual modulation, the signal strength varies with Earth's orbit. As Earth moves through the galaxy's dark matter halo, we should encounter more dark matter particles when moving into the wind versus moving with it. DAMA sees this pattern. For over 20 years they've maintained, we detected dark matter. The problem? No other experiment can replicate it. LUX, Xenon, Panda X, all more sensitive detectors, see nothing in the parameter space DAMA claims. 2 possibilities. DAMA is detecting dark matter through unknown physics. DAMA is seeing systematic error they don't understand. Most physicists lean toward number 2. 2000. CDMS, Cryogenic Dark Matter Search, sees 2 candidate events. Excitement. Later, statistical fluctuation. 2013. CDMS-2 sees 3 events in silicon detectors. Could be dark matter. Later, Probably not. 2020. Xenon 1T sees unexpected electron recoil excess. Dark matter? Likely tritium contamination. The pattern repeats. Detector sees unexpected signal. Matches some dark matter predictions. Papers published. Press releases issued. Deeper analysis reveals alternative explanations. Retraction or downgrade to consistent with background. This is why scientists are cautious. Why pay attention to LUX-ZEPLIN signal? 1. Sensitivity. LZ is one of the most sensitive dark matter detectors ever built. It can detect interactions down to incredibly small energies. 2. Background rejection. Multiple signal types, scintillation plus ionization, allow discrimination between particle types. 3. Shielding. A mile underground plus layers of shielding reduce cosmic ray background by a factor of 10 million. 4. Statistics. They've collected years of data. This isn't a single event, it's analyzed in context of millions of events. But one event is not a discovery. One event is a curiosity. As of early 2025, LZ continues running. The question: will more events appear with similar characteristics? Or was this one a fluke? Discovery requires multiple events with consistent properties. Statistical significance, 5 sigma, 1 in 3.5 million chance of being random. Independent confirmation from other experiments. Other experiments are watching. If dark matter is really interacting at this energy and rate, they should see it too. Science doesn't accept single events. It demands reproducibility. Why do we think dark matter exists? 1993. Fritz Zwicky studies the Coma galaxy cluster. He calculates how much mass it should contain based on visible galaxies. Then he measures how fast those galaxies are moving. Problem: they're moving too fast. At their observed speeds, galaxies should fly apart, unless there's 400 times more mass than we can see holding them together. Zwicky calls it dunkel materia, dark matter. 1970s. Vera Rubin measures rotation curves of spiral galaxies. Stars far from galactic centers orbit too fast. According to Newton's gravity and visible mass, outer stars should move slower. They don't. Either there's invisible mass, dark matter, or gravity doesn't work the way we think. We can see dark matter indirectly through gravitational lensing. Mass bends space-time. Light follows curved space-time. Massive objects act as lenses, distorting light from background galaxies. By measuring the distortion, we map where mass is, whether we can see it or not. The Bullet Cluster. 2 galaxy clusters that collided. Visible matter, hot gas emitting X-rays. Concentrated between the clusters, slowed by collision. Gravitational lensing, total mass. Concentrated where the galaxies are, passed through each other. The mass and the light don't match. Most mass is dark, invisible but gravitationally present. This is our strongest evidence. Dark matter behaves like matter, clumps, has gravity, but doesn't interact with light. We know dark matter exists gravitationally. We don't know what it is. What we know makes up approximately 85% of universe's matter. Doesn't emit, absorb, or reflect light. Interacts gravitationally. clumps into halos around galaxies, was present in early universe, affects cosmic microwave background. What we don't know: what particles it's made of, its mass, whether it interacts via any force besides gravity, why the dark to visible matter ratio is approximately 5:1. The possible mass range for dark matter particles spans over 100 orders of magnitude, from ultralight axions to primordial black holes. That's a lot of parameter space to search. WIMPs, weakly interacting massive particles. Predicted by supersymmetry theories. Mass 10 to 1000 giga-electron volts. Would interact via weak nuclear force, rarely but detectably. Axions, ultralight particles. Predicted by quantum chromodynamics. Would interact with photons in strong magnetic fields. Sterile neutrinos. Hypothetical heavy neutrinos that don't interact via weak force. Mass, kilo-electron-volt range. Primordial black holes, formed in early universe. Not particles, tiny black holes. Controversial whether they explain all dark matter. Each candidate requires different detection strategies. LZ and similar detectors hunt WIMPs. Other experiments target axions, sterile neutrinos, etc. If WIMPs exist at predicted masses and interaction rates, trillions pass through your body every second. Maybe one per year interacts with an atom in your body. WIMPs interact less frequently than neutrinos, and neutrinos are famously ghostly, passing through entire planets without touching anything. To detect something that rare, you need large detector. More target atoms equals more chances. Ultra-pure materials. No radioactive contamination. Deep underground. Shield from cosmic rays. Long observation time. Wait for rare event. Precise discrimination. Distinguish signal from background. Even with all this, a year of data might yield 0 to a few candidate events. Everything is radioactive at some level. The rock surrounding the detector contains uranium, thorium, potassium, decaying constantly, emitting neutrons and gamma rays. Cosmic rays penetrate underground, creating secondary particles. The detector materials themselves contain trace radioactivity. Dark matter signal and background noise overlap in energy range. Your job? Find the few dark matter needles in the haystack of background. Statistical confidence requires understanding your background extremely well, seeing excess events above predicted background, 5 sigma significance, 1 in 3.5 million chance of random fluctuation. This is why a single event proves nothing. Earth's surface. Approximately 10,000 cosmic rays per square meter per second. Cosmic rays create secondary particles when hitting atmosphere, muons, neutrons, pions. These particles penetrate deep into matter. 1 meter of rock reduces cosmic rays by a factor of approximately 10. 10 meters, factor of approximately 10,000. 1,000 meters, 1 kilometer, factor of approximately 10 million. LUX-Z at 1,478 meters depth. Cosmic ray muon rate reduced to approximately 1 per square meter per day. Major dark matter experiments are all deep underground. Xenon, Gran Sasso, Italy, 1,400 meters depth. SNOLAB, Canada, 2,070 meters depth. Panda X, Jinping, China, 2,400 meters depth. The deeper, the quieter the background. Beyond rock shielding, detectors have additional layers. Water tank, surrounds detector, blocks neutrons, also acts as active veto. Particles creating signals in water are rejected. Lead, blocks gamma rays from radioactivity in rock. Polyethylene, moderates, slows down any remaining neutrons. Copper, low radioactivity structural material, specially selected. Xenon self-shielding. Only central fiducial volume is analyzed. Outer xenon catches particles coming from outside. Events near detector edges are ignored. Events in the pure central volume are analyzed. Each layer reduces specific backgrounds. Combined, factor of 10 to the power 12 reduction in unwanted signals. Modern xenon detectors are dual-phase, liquid and gas xenon in same vessel. When a particle interacts with liquid xenon, 1. Immediate scintillation. Xenon atoms emit ultraviolet light, S1 signal. 2. Ionization. Interaction frees electrons. 3. Electron drift. Electric field pulls electrons upward through liquid to gas phase. 4. Electroluminescence. Electrons crossing into gas create second light pulse, S2 signal. S1 amplitude tells energy of interaction. S2 amplitude tells how many electrons were freed. S2/S1 ratio distinguishes particle types, nuclear recoils, dark matter candidate, versus electron recoils, background. S2 position, XY location in detector, from pattern of light on top photomultipliers. Drift time, Z depth in detector, time delay between S1 and S2. Full 3D event reconstruction from light signals alone. Nuclear recoils, atom itself recoils. Low S2/S1 ratio, less ionization per energy. Electron recoils, electron knocked off atom. High S2/S1 ratio, more ionization. Dark matter, if WIMP causes nuclear recoils. Most backgrounds cause electron recoils. This discrimination is powerful. Rejects 99.9% plus of background events, but not perfect. Some nuclear recoil backgrounds remain. Neutrons from radioactivity, neutrons from cosmic rays, coherent neutrino scattering, irreducible background. The December 2024 event sits in the nuclear recoil region. Energy consistent with WIMP. Location in fiducial volume. Everything checks out, except it's one event. In particle physics, discovery requires 5 sigma statistical significance. What does that mean? If your signal is 5 standard deviations above expected background, the probability it's a random fluctuation, 1 in 3.5 million. Or stated differently, if the signal were random noise, you'd have to repeat the experiment 3.5 million times before expecting to see this by chance once. 3 sigma. 1 in 740 chance. Interesting. Not conclusive. 5 sigma. 1 in 3.5 million. Discovery threshold. Why so stringent? Because physics has history of 3 sigma discoveries that disappeared with more data. The Higgs boson was only announced after 5 sigma significance from 2 independent detectors, ATLAS and CMS at LHC. One event in LZ's nuclear recoil region. Expected background events in this energy range over observation period. 0.5 events. Observed, 1 event. Statistical significance, less than 2 sigma. This is consistent with dark matter. It's also consistent with random background fluctuation. You can't claim discovery from this. You can say, interesting. Let's keep watching. Real discoveries have common features. 1. Reproducibility. Same experiment, repeated, sees same signal. 2. Independent confirmation. Different experiments, different teams, different locations, all see it. 3. Consistency. Signal matches theoretical predictions across multiple tests. Neutrinos, 1950s. Predicted 1930. Detected 1956. Multiple experiments confirmed. Gravitational waves, 2015. Predicted 1916. Detected 2015 by LIGO. Dozens of detections followed. Higgs boson, 2012. Predicted 1964. Detected 2012. 2 independent detectors, ATLAS, CMS, saw it simultaneously. Single experiments can claim evidence. Discovery requires confirmation. Multiple experiments hunt WIMPs simultaneously. LUX-ZEPLIN, 7 tons Xenon, South Dakota. Xenon NT, 8 tons Xenon, Italy. Panda X4T, 4 tons Xenon, China. Super CDMS, different technology, cryogenic germanium and silicon, Canada. If dark matter is real and interacts at detectable rates, multiple experiments should see events in similar energy ranges at similar rates, accounting for detector mass and exposure time. So far, no experiment has compelling excess above background. LZ's 1 event, not yet confirmed. Xenon NT and Panda X are analyzing their data from same time period. If they also see excess events with similar properties, excitement justified. If they see nothing, LZ's event is likely background. False positives in dark matter detection come from 1. Misunderstood backgrounds. Thinking you've accounted for all backgrounds, but missing one. Example: Xenon 1T's 2020 excess. Initially exciting. Later, likely explained by tritium contamination. Radioactive hydrogen from cosmic ray interactions. 2. Statistical fluctuations. With enough data, rare events happen. If you predict 0.5 background events and see 1, that's not surprising. 3. Systematic errors. Equipment behaving unexpectedly. Electronic noise mimicking signal. Light leaks. Temperature fluctuations affecting response. 4. Analysis bias. Consciously or unconsciously, analysts might optimize cuts to enhance signal-like events. This is why blind analysis is crucial. Define cuts before looking at signal region. Dark matter detection is competitive. High stakes. Nobel Prize awaits whoever makes the discovery. Funding depends on producing results. Careers advance with significant findings. This creates pressure to publish positive results, even if marginal. Scientists are human. They want to believe their signal is real. This is why the process has safeguards. Peer review before publication. Independent replication. Adversarial scrutiny from competing teams. Statistical thresholds, 5 sigma. The system works, eventually. But it's slow. Frustrating. Necessary. When LZ has results to report. 1. Internal review. Collaboration. 100 plus scientists. Reviews analysis. Challenges assumptions. Looks for errors. 2. Paper draft. Submitted to journal. Physical review letters, Nature, etc. 3. Peer review. Experts not on the team evaluate. Are methods sound? Are backgrounds properly estimated? Are statistical claims justified? Are alternative explanations addressed? 4. Revisions. Respond to reviewers. Provide additional analysis. Clarify. 5. Publication. If passing review. This takes months, sometimes years. Meanwhile, rumors leak. Conference talks hint at results. Media reports possible detection, but official claim awaits peer review. When do you announce? Too early. Risk embarrassment if wrong. Damage credibility. Too late. Competitors might announce first. Miss opportunity. LZ's approach, common in field. Present preliminary results at conferences. Caveat heavily. Emphasize need for more data. Full claim of discovery. Only after 5 sigma significance and peer review. The December 2024 event. Mentioned in internal discussions. Not yet published. Not yet confirmed. We're in the waiting phase. If dark matter is directly detected, Nobel Prize in Physics. Guaranteed. Not just to individual scientists, to the collaboration, the technology pioneers, the theoretical predictors. Historical precedent. 2013. Higgs boson discovery. Higgs, Englert. 2017. Gravitational waves. Weiss, Thorne, Barish. 2015. Neutrino oscillations. Kajita, MacDonald. Dark matter would join this pantheon, solving one of the deepest mysteries in physics. Knowing dark matter's identity would transform physics. 1. Particle physics. Validators beyond standard norm of physics, supersymmetry, extra dimensions, whatever framework predicted it. 2. Cosmology. Precise dark matter properties constrain early universe models, structure formation, galaxy evolution. 3. Astrophysics. Dark matter distribution in galaxies, clusters, cosmic web becomes mappable in detail. 4. Fundamental physics. New interactions, new forces, new symmetries to explore. 5. Technology. Ultra-sensitive detector technology has applications. Medical imaging, nuclear security, material science. It's not just solving a mystery. It's opening an entirely new field. Alternative hypothesis. Maybe there's no dark matter. Maybe gravity works differently at large scales. MOND. Modified Newtonian Dynamics. Proposed by Mordechai Milgram, 1983. Idea. Below certain acceleration threshold, gravity doesn't fall off as 1/r². It falls off slower. MOND successfully predicts many galaxy rotation curves without invoking dark matter. But MOND struggles with galaxy clusters. Needs more modification. Bullet cluster. Lensing mass doesn't match visible matter location. Cosmic microwave background. Pattern requires dark matter in early universe. Large-scale structure formation. Most physicists favor dark matter because it explains more phenomena consistently. But if dark matter detection keeps failing, MOND or other modified gravity theories gain credibility. Dark matter experiments have been running for 30+ years. Results so far? Nothing conclusive. Each null result rules out part of parameter space, specific WIMP masses and interaction strengths. We've ruled out most natural WIMP models. Remaining possibilities. Dark matter is lighter than expected. Dark matter is heavier than expected. Dark matter interacts even more weakly than predicted. Dark matter isn't WIMPs at all. Axions, sterile neutrinos, primordial black holes. Dark matter doesn't exist. Gravity is modified. Each null result narrows the search, but doesn't end it. If current detectors don't find dark matter, next generation will be bigger. Darwin, 40 to 50 tons of xenon, 10 times larger than current. Underground in Europe, planned for early 2030s. Argo, similar scale, US or Canada. Next generation super CDMS, larger mass, lower energy threshold. These detectors will reach neutrino floor, where solar neutrinos create irreducible background that can't be shielded. If dark matter isn't found by then, we'll need to rethink either dark matter properties or detection strategy. Back to LZ's December 2024 event. As of early 2025, no confirmation, no replication. Not enough data for conclusions. Scientists are watching. Detectors are running. Data is accumulating. Maybe more events will appear with consistent properties. Maybe not. Maybe other experiments will see similar signals. Maybe they won't. This is science at the frontier. Uncertain, patient, rigorous. The most important signal we're not sure we saw. Did we find dark matter in 2025? Honest answer, we don't know yet. We have one interesting event, consistent with predictions, also consistent with background. This is the gap between science and headlines. Headlines want, dark matter discovered. Science requires, event observed, consistent with dark matter hypothesis, awaiting confirmation. Statistical significance insufficient for discovery claim. Continued observation necessary. Not as catchy, but honest. The story of dark matter detection isn't one moment of discovery. It's decades of building more sensitive detectors, ruling out backgrounds, accumulating data, refining theories, being wrong, learning, trying again. And somewhere, deep underground, detectors wait for the next flash, the next event, the next piece of evidence. 85% of the universe's mass remains invisible, but we're looking. This is Cosmic Canvas, where we investigate the universe's deepest mysteries with patience, skepticism, and scientific rigor. Until next time, question the headlines, demand the data, understand the process.